Hello. The topic for the session is quantum entanglement. So let's begin with a brief overview of the session. So quantum mechanics is a mathematical framework for studying atomic and subatomic systems. And in fact, that underlies a lot of things like chemistry and lasers and other things which you might come across in your studies. Now, Albert Einstein is one of the founders of quantum mechanics, and he believed that while the theory was essentially correct, it was not quite complete in his eyes, and it did not provide a complete description of nature. So he had this kind of nagging doubt that something was missing from the theory. And so in 1935, Einstein and his colleagues Boris Podolsky and Nathan Rosen, EPR over here, published a paper that tried to show why that was true, why quantum mechanics was incomplete. And this is a very famous paper which is entitled, Can Quantum Mechanical Description of Physical Reality be Considered Complete? And the keyword, of course, here is complete. He was not doubting the utility or correctness of theory, but just doubting the completeness. Now, the arguments in this paper are based on the notion of quantum entanglement, and that's the topic for this session. So in this session, we discuss a simple example of quantum entanglement using ideas from linear algebra, what we studied so far, like things like inverses and dot products and all that, and the modern theory of quantum computation, which gives us some nice examples for studying the topic. Okay, so let's begin with the notion of a quantum bit. So quantum bit, or qubit for short, is a simple quantum system that has got only two states, two basic states, 0 and 1. So for example, you might have an electron which is either in the spin up state or the spin down state, but of course those are just the basic states of the electron, like you see over here, and that's kind of symbolic. And the point over here is that the state of the qubit at any time will then be what they would call a linear superposition of the basic states. Now that's what you would call a linear combination in linear algebra. So the vector v for the state will be a linear combination a times the first state and b times the second state. Now these weights a and b over here must satisfy the relation absolute a square plus absolute b square equal to 1. Now you think of these as being complex numbers, but for our purposes, you might as well think of them being real numbers. So a and b could be arbitrary, but their squares must add up to 1. So here are some simple examples. This first one over here is in coordinates, the state 1, 0, which is just the state 0. The second one is 0, 1, which is the state 1. The last one over here is a kind of symmetric linear combination of them. So 1 over square root of 2 times the first one and 1 over square root times the second one. But of course, if you square these and add up, you get back 1 just as required. Okay, now the second piece of quantum theory is the notion of quantum evolution. So if you have a quantum system at any time, then as it evolves in time, then that evolution is described by unitary transformation u. So that's a bit like an orthogonal transformation, except that you have a conjugate away because you've got complex numbers. So you have u times the conjugate transpose of u is equal to the identity matrix. So let's say if the state time t1 is given by v, then at late time t2 it will be given by w equal to u dot v or u times v. So for example, here is an example of u. Let's check that's unitary. That's correct. And let's see what happens to it when you act on the basic state. So if it acts on 1, 0, then it kind of mixes up the state into a combination of the two states 0 and 1. And the same thing if you do 0 and 1, but you get a negative sign over here. Now the main point over here is that the evolution of the system is a reversible process because this matrix U is an invertible matrix. You can see that over here. So quantum evolution is a reversible process and is given by a unitary transformation. On to the next piece of quantum theory, and that's the one that creates the most difficulty, is an idea of quantum measurement. So quantum measurements are described by a set of projection operators onto the various basic states. Those are just the same projection operators we studied earlier in the course. So for example, if you've got a single qubit, then here are two operators. That's the first matrix. The second matrix, they are projection matrices. And if you apply the first one, this one over here, to a comma b, then it kind of throws that into the state a comma 0. And if you apply a second one, it throws in state 0 comma b. So those are projections onto the first and the second basic state. Now, of course, both those will not happen. They'll happen with some probabilities. And those probabilities are given by the square of a and square of b absolute value. Assume, of course, that the squares over here add up to 1. Now, the key point is that these operators, unlike the evolution operators, are not invertible. In fact, their determinants are 0. So unlike quantum evolution, quantum measurement is not a reversible process. So when you do a measurement, you kind of lose information and you cannot go back from where you came. Okay, so now you move on to the concept that's of crucial importance for us over here, and that's the idea of quantum entanglement. So let's say you have a pair of qubits, not just one qubit, but a pair of qubits, each of which has the states 0 and 1 to work with. And let's say you allow these qubits to interact for some time. And then, of course, you separate them. So what happens is that after this interaction, the system of qubits will be a linear superposition of 4 states, 0, 0, 0, 1, 1, 0, and 1, 1, where, of course, the first entries over here label the first qubit and second ones label the second qubit. So, for example, here is a linear superposition of the first and the third states. So first and third over here would mean that you're taking the state 0, 0 and 1, 0, as you can see over here. Now, this state is not so interesting because it can be kind of factored. After all, it has the second qubit in 0 state in both the terms over here. So this is not so interesting. A much more interesting combination is when you take the first and the fourth states. So if I take 0, 0 and 1, 1, then I get the state V1 over here. And you see now that you really cannot factor to it. So it cannot be factored because you actually have no way of separating out the qubits in this combination over here. Okay, so this over here is an example of an EPR pair, an Einstein-Podolsky-Rosen pair. So these EPR pairs are in fact the simplest examples of quantum entanglement. So we've learned about EPR pairs over here in quantum entanglement, and now we can ask the question, why did Einstein object to this? And why did he talk about spooky action at a distance? To understand that, recall that you have these 4 basic states for a pair of qubits, 0, 0, 0, 1, 1, 0, and 1, 1. And again, consider the entangled pair from the earlier slide. Now, the point is that if you want to observe the second qubit in 0 state, the probability of that happening is 1/2. After all, that's roughly 1/2 of the linear combination. And then we need a measurement operator for doing that. So this is the measurement operator for measuring the 0 state for the second qubit. And the question is, why do this very peculiar combination over here? Well, the 1 and the 1 over here in the first and third places because the 0 and the 0 are there in the first and the third combination over here. Okay, so now once you apply this operator to V1, what you see is it kind of gets collapsed into the first option over here, which is 0, 0. So the measurement collapses the EPR pair into the 0, 0 state. So the first qubit will now be in the 0 state after measurement, irrespective of the distance that separates the qubits at time of measurement. So remember, you measured the second one, but the first one actually goes in 0 state, and Einstein was very puzzled by this, and he spoke about spooky action at a distance. After all, there is no discussion of distance over here, and so how could that happen? Now the question is, why did Einstein say it? Well, the point is that between 1905 and 1915, he had worked very hard to rid Newtonian gravitation of action at distance, and now he was noting the same thing in quantum mechanics, and he just could not accept it. So Einstein had to reconcile his views on quantum mechanics and general relativity, and he said, no, we cannot allow spooky action at distance, and this led him to work on his unified field theory. Now, the question is, was there something to Einstein's argument or not? Well, when I was a graduate student, I recall attending a conference organized by Roger Penrose, and at that conference, there were lots of excellent speakers talking about the foundations of quantum mechanics, but one of the speakers was not a theoretician, he was actually an experimentalist, and that was Alain Aspect. So Alain Aspect performed a very famous experiment to see what would happen if we actually tested quantum entanglement. So around 1982, Alain Aspect and his colleagues performed experiments to observe quantum entanglement of photons, which is the other possibility for these very simple EPR pairs. And the goal of the experiment was to test the violation of inequalities that were stated early on by John Stuart Bell, an Irish physicist. So here's the schematic representation for Aspect experiment. So basically you have a source which produces these EPR pairs, and then those two are polarized over here, and then you observe what happens at those two ends over there. Now, what happened was that Aspect experiment was in fact the first quantum mechanics experiment to demonstrate the violation of Bell's inequalities in a very conclusive manner, and this experiment is now seen as a proof of the quantum mechanical nature of reality. So it does look like nature respects quantum mechanical laws and we must accept those. So that brings me to the end of this session, and the main point is that entanglement is a uniquely quantum phenomenon that occurs in multi-qubit systems. Now, once it was established that this is actually true in nature, then people started applying this idea, and today quantum entanglement is used in applications such as quantum teleportation, which relies heavily on quantum entanglement. But of course, from our point of view, the main point is that linear algebra, which you've learned in this course, provides a really elegant way of understanding entanglement and other quantum phenomena. So linear algebra will help you a lot to understand quantum mechanics, and of course lots of the subject, whether it be data science or statistics or economics. So do study it. It's a great subject to learn. I'll stop over here. Thank you very much.